Have you ever seen those really ugly domes on top of an otherwise beautiful Jaguar? Yeah, those are actually LIDAR sensors. LIDAR stands for light detection and ranging. And in this video, I'll go through exactly how LIDAR works, what kind of wavelengths are used, what kind of detectors are best suited for different wavelengths, and how systems based on mechanical LIDAR and solid-state LIDARs work. Hi, my name is Vikram Shekhar and I write a Substack called Vik's Newsletter, which covers a whole lot about semiconductor technology. On this YouTube channel, I describe a short explanatory version of what I usually write on the Substack. So if you want much more in-depth content, head on over to the Substack, whose link is right up here. The first question we need to ask ourselves when it comes to LiDAR technology is it even required for autonomous driving? Now, there are two schools of thought on this. Some say yes, LiDAR is absolutely essential. And the other school, primarily stemming from Tesla's and Elon Musk, says no, it's not required. And you can do autonomous driving entirely with cameras. Now, the argument for the camera-only approach is that humans don't exactly have LiDAR sensors attached to our heads. So if we are able to drive with just our eyes, then so should cars. But the downside to this approach is that cameras just don't have the capabilities of the human eye, which has evolved over millions of years. So the way to augment vision in a self-driving car is to use technology other than cameras, which in this case could be LiDAR. Now, the argument against LiDAR is that it is really expensive. And this was true because the original Waymo taxi has a sticker price in the range of $200,000, which is way too expensive. So if the camera-only driving approach works out better, it can be far more economical for autonomous driving to be incorporated in a whole lot more scenarios. However, the cost of LiDAR technologies has been continuously coming down. So how does a LiDAR system exactly work? The idea is very simple if you think of how a bat does echolocation. A bat sends out an acoustic signal which then travels to a far-off object, gets reflected and comes back and is heard by the bat's ear. And between the time the signal is emitted by the bat to when it's received, the bat is able to tell how far the obstacle lies and is able to navigate around them. In LiDAR, the principle is exactly the same. And this principle of ranging is called direct time of flight. So the signal is emitted by a transmitter and it is usually in the range of infrared light. This infrared light reflects off of a far off object and comes back to a photodetector, which acts as the receiver in this case. The time difference between when the infrared light was emitted to when it is received, when multiplied by the speed of light, gives basically twice the distance that the signal has traveled to and from the obstacle. And so simply dividing that by 2 gives you the distance to an object. Direct time of flight LiDAR is the most commonly used LiDAR technology because it is quite simple. There are other more complicated schemes that I'll briefly mention later, but for the most part, direct time of flight sensors provide reasonably good performance even up to the range of 200 to 300 meters ahead of a vehicle that is moving at highway speeds. Now let's talk about what light wavelengths are actually used in LiDAR. There are two primary choices one can make. One is 905 nanometers, also called near infrared. The other is 1550 nanometers, also called shortwave infrared. And deciding which one to choose depends on the output power of the lasers that generate this infrared light, the sensitivity of the detectors that detect them, and how much interference this wavelength faces in a terrestrial environment. Now, while we're talking infrared light, one of the biggest sources of interference right here on Earth is the sun. Luckily for us, if you look at the spectral irradiance from the sun on Earth and sort it out according to wavelength, there are a few wavelengths where the interference from the sun is actually much lower. And this is primarily caused by the absorption of these wavelengths in the upper atmosphere by water vapor and other environmental factors. This means that luckily these wavelengths get filtered out by our upper atmosphere and don't reach the ground. And 905 nanometers and 1550 nanometers are within these spectral windows, which make these wavelengths useful for LIDAR detection on Earth. What's nice about 905 nanometer is that the laser sources available at this wavelength can output significant amounts of power, which makes it much more useful for ranging over long distances if we can emit a high enough amount of laser light. At 905 nanometers, the detectors are also much more sensitive, which means you get an overall better signal to noise ratio when you use 905 nanometers or near infrared light. However, there are two downsides to using this. 905 nanometers is much more dangerous to the human retina because it lies very close to the range of visible wavelengths by the human eye. Secondly, right around 905 nanometers, there are plenty of sources of interference from natural sources. Therefore, switching to 1550 nanometers mitigates some of these problems. For one, there is lower interference from wavelengths around 1550 nanometers. Also, because it is so much farther away from the wavelengths of light that the human eye can actually see, 1550 nanometers is a lot safer in terms of eye safety. But the choice of wavelength also depends on the kind of photodetectors we use. So let's look at that next. Avalanche photodiodes, or APDs, are the most commonly used form of detectors in LIDAR systems. APDs are essentially semiconductor junctions which generate a whole lot of electrons and holes in response to light being incident upon them. Now, the kind of semiconductor material used makes the APD sensitive to different wavelengths. For example, a silicon APD is really well suited to the 905 nanometer wavelengths and is much cheaper to implement because it's a simpler material. However, at 1550 nanometer, one has to use more complicated semiconductor materials like indium gallium arsenide. But a really popular detector used in LIDAR systems is what is called a single photon avalanche diode, or SPAD. SPADs are really unique devices. They are operated in what is called Geiger mode, which means that the semiconductor junction is biased very close to breakdown, such that even a single photon that arrives at the semiconductor junction produces a whole lot of electrons which can be detected as current. With these single photon detectors, one can detect photon arrivals to the accuracy of 1/1,000,000th of a second, which makes the detection process through direct time of flight extremely accurate. Now, I did mention that there is another technique other than direct time of flight ranging for LIDAR, and that is called frequency modulated continuous wave, or FMCW LIDAR. The idea behind this LIDAR is that instead of using just one wavelength, you use a whole range of wavelengths, and instead of sending a single burst of a single wavelength of light, you send what is called a chirp signal. In a chirp signal, the wavelength of light emitted continuously increases for a given interval of time. And that whole chirp signal travels to the object, gets reflected off of it, and is detected by the receiver. Because there is a time delay between the transmitted chirp and the received chirp, at any given instant within the chirp, there is a wavelength difference between the transmitted and the received chirp. And by finding the beat frequency between these transmitted and received chirps, you can estimate the distance to the object. We won't go much more into this, but FMCW LIDAR is much less prone to interference from neighboring light sources and can actually be very accurate. Let's talk about LIDAR systems. It's just not enough to send a signal from one point, have it reflect and come back. What is usually done is that you need to map out the entire space around you, which means that the light source and the detector need to be steered mechanically or electronically so that all the information within the field of view is captured. Now, the mechanical dome you see on top of a self-driving car simply has a motor that rotates the light source and the detector in 360 degrees at a really rapid rate. That way, the LiDAR is sending bursts of light in all directions and receiving it and mapping out the entire space around it. These motors are not exactly inexpensive, and mechanical motors are subject to wear and tear over time. So another alternative approach has been proposed where instead of moving the light source itself with the motor, you actually shine the light source onto an array of very tiny microscopic mirrors called MEMS mirrors. And then you mechanically move the MEMS mirrors around so that the light is being reflected off the MEMS mirror into various directions, and then you can capture the reflected light and map the area around you. There are other approaches that don't actually use mechanical steering. One such approach is called a flash LiDAR. A flash LiDAR is much like a photographic camera, where you have a flash, or in this case, an array of light sources. You send a whole bunch of light towards an object. It is received by another array of detectors, and you capture the whole image in one go. However, the rate at which you take these flashes should be really quick in order for you not to miss any detail in a fast moving vehicle. The last option is what is called an optical phased array LiDAR. Here there are many optical elements or lasers, and each one of them emits at a slightly different time from the one next to it. By adjusting how much delay is there between each of these laser elements, one can steer the beam of light electronically and capture an entire field of view. Alright everyone, that's it for this video. I hope you learned something about LiDAR systems today, and the next time you get a chance to ride in one of these autonomous cars, I hope you get a chance to appreciate all the technology at work around you.